Okay, today we're going to learn about another important series called the harmonic series. This is, in fact, one of the most important divergent series that we'll learn in this unit. Okay, the harmonic series is the summation as n equals 1 to infinity of 1 over n, or 1 over k. 1 over n is what it should say there, which is a series 1 plus 1/2 plus 1/3 plus 1/4 plus blah, blah, blah. And this actually diverges. It doesn't approach any value. Okay. And so this is a harmonic series is always divergent. Okay, now we're going to look at a couple of theorems that's going to help us out. If a sub n is less than or equal to a sub 2, which is less than or equal to a sub 3, which is less than or equal to a sub 4, which is a non-decreasing sequence, a monotonic sequence that we talked about before, there are two possibilities. If there is a constant m such that a sub n is less than or equal to our m value for all n in that case, the sequence converges. And it converges to a limit of L, satisfying that the L must be less than or equal to our upper bound of M. If no such constant exists, in the case, the limit as n goes to infinity of 2 to the n, it goes to infinity, if there's no upper bound, basically. Or if a series a sub 1 is greater than or equal to a sub 2, which is greater than or equal to a sub 3, which is another way of saying a non-increasing sequence, it has two possibilities. It could have a lower bound where a sub n, there exists a constant m such that a sub n is greater than or equal to m for all n, in which case the sequence converges to a limit L, satisfying that that limit L is greater than or equal to m, because this is a lower bound. If no such value exists, then it diverges to negative infinity. So let's look at a harmonic series and show that it diverges, prove that it diverges. Okay, so if I take my first partial sum, that would be 1 over 1, which is 1. My second partial sum would be that 1 plus 1/2. My third partial sum would be 1 plus 1/2 plus 1/3. And my fourth partial sum is going to equal to 1 plus 1/2 plus 1/3 plus 1/4, etc. So this is a non-decreasing monotonic sequence. So I need to see if it's non-decreasing. We're going to be looking for a upper bound. See if this has an upper bound to it. Okay, now this is something you're going to use comparison on this one in a way. And this is something that's kind of cool that kind of happens when you're working with sequences. And here, just in case you're not sure what non-decreasing monotonic sequence is, I'll just put it down here. So what I'm going to do is I'm going to look at the even or powers of 2. So I'm going to look at the partial sum s of 2, s of 4, and s of 8. Okay? And you'll see why as I work through this. And so that would be my s of 4 partial sum. And then I'm going to compare this to a value. And these values I'm going to choose to compare this to is going to be well chosen. That's my s of 8. Now notice, I could compare 1/3 plus 1/4, what I put in parentheses there, to 1/4 plus 1/4, just repeating. And that'll give me a 1/4 plus 1/4 is 1/2. And I know that 1/4 plus 1/4 is going to be less than 1/3 plus 1/4. Okay, so I'm going to replace that 1/3 in the parentheses here with 1/4. And I'm going to say that that is a true statement, that the left-hand side of that s of 4 is less than. Now, I'm going to do the same thing on s of 8. And then for the 1/5, 1/6, 1/7, 1/8, I'm going to replace those all with 1/8. So it's 1/8 plus 1/8 plus 1/8 plus 1/8. That's 4/8, which is a half. So I'm adding a half again. So just like 1/4 plus 1/4 was a half. So I'm adding a half each time. And so I can say, okay, that's going to be that's going to be less than my right-hand side. So I'm going to have my right-hand side greater than that value. Okay, so notice that if I s to the 4 here on my right-hand side, I got 1 plus 1, a half plus a half. And then over here, I fixed that mistake there. I have 1 plus 1 plus a half. So notice the pattern that's going on. Okay. So I could rewrite this as 1 plus 3 halves. So I have 1 plus 1, 1 plus 1, 1 plus 1 half. Let's do, so S of 4 I could rewrite as 1 plus 2 over 2. S of 8 I can rewrite as 1 plus 3 over 2, that right-hand side of it. That is less than our left-hand side. Let's do one more, S of 16. So if I did the partial sum, if I wrote out the sequence, the series, S of 16, that'd give me 1 plus 1 half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus, and then we'll put the rest of them in another group, 1/9, 1/10, 1/11, 1/12, all the way up to 1/16. Now that's going to be greater than, if I substitute in place of that 1/3, 1/4 to get 1/4 plus 1/4, which is a half. If I substitute in place of that 1/5, 1/6, 1/7, 1/8 to get another half, and I replace all of that 1/9 through 1/15 with 1/16, so I can get another 1/2, because that'd be 8/16. Okay, so now I notice that this one has a, so notice the pattern here. Our S of 2 term was 1 plus a half. Our S of 4 term was 1 plus 2 over 2. Our S of 8 term was 1 plus 3 over 2. Our S of 16 was 1 plus 1 plus 4 over 2. So notice that we have our S of 2 to the n power is greater than 1 plus 1 over n to the 2. Okay, so let's find the limit of that 1 plus n over 2, that right-hand side of this. And we see that limit is infinity. So if our sum is greater than infinity, our conclusion is it must also go to infinity. So therefore, as n goes toward infinity, our sum, S of n, diverges. Isn't that cool proof? All right, let's talk about, now that we know what infinite series are and some examples of infinite series, let's talk about some properties of infinite series so that we can evaluate some of these summations. So if A sub n summation is A and B sub n summation is B, if I take the summation of a constant C times it by A sub n, that would be the constant C times it by that sum of BK. So that's just going to give us C times BK. And now if I add two sums together, I can just add their sums. Okay, if I take this the summation of A sub n plus minus B sub n, I would just subtract their sums. So if I ask you to find the sum of the series, the summation of k equals 1 to infinity of 3 to the k, 3 over 4k, now I'm going to distribute the summation, so that's minus the sum of k equals 1 to infinity of 2 over 5 to the k minus 1 power. Do you notice that this is a geometric series that we learned in our last video? I could rewrite this so that in that geometric series format as summation of k equals 1 to infinity of, bring out that 3/4, times it by 1 over 4 to the k minus 1 power. So my A is 3/4 and my R is 1/4. And so the absolute value of 1/4 is 1/4. 1/4 is it's less than 1. So I know that by our knowledge of geometric series that this series converges. And so I can find the sum of that first fraction by using our A over 1 minus R to get, so that gives us 3/4 over 3/4, which is 1. Now let's look at the other half. So we still have that minus the summation of k equals 1 to infinity of 2 over 5k minus 1. This is another geometric series. I can factor the 2 out, and I can rewrite that as 2 times 1 over 5 to the k minus 1 power. So my A is equal to 2. My R is equal to 1/5. Absolute value of 1/5 is 1/5. 1/5 is less than 1, so this converges. The sum it converges to, we're going to use that formula A divided by 1 minus R. And so that's going to give us 2 divided by 4/5. Flip and multiply the bottom fraction. It gives us 10/4, which simplifies down to 5/2. So my first summation sums to 1 minus my second summation goes to 5/2. So my answer is going to be 1 minus 5/2, which is just negative 3/2. All right. Now looking at this one, I can factor out that constant 5 and rewrite this as summation of k equals 1 to infinity of 1 over k. Recognize that that is a harmonic series, and we know that harmonic series diverges, and therefore this one diverges.